All right, statisticians, last week was pretty full of conceptual lessons, and this week is going to be much more practical. We're going to be learning to use the calculator more for a lot of its shortcuts, and we'll be carrying out what are some fairly laborious formal processes for performing significance tests. And so we're going to begin with something that you should remember when we were making confidence intervals before. Remember how we talked about a kind of four-step process where we thoroughly showed all our work so that everything was super clear and all our methods were justified? That four-step process we sort of remembered was based on 4 words. Some people had different fun ways of memorizing it. For instance, school, police, do cocaine. Good times. Which is not true, right? I assume. But we talked about the 4-step process where we start by stating and then planning and then doing and then finally concluding, right? We had this 4-step process where we that we use to justify our methods for making confidence intervals. We'll have the same kind of process for a significance test. I'm just going to reveal the whole thing all at once here. Boom. When we're carrying out a significance test, we're going to have this same 4-step process. So jot down all these things in your notes, but let's just quickly review, right? So just like before when we stated, we'll always start by defining whatever parameter it is that we're actually dealing with, and we'll make sure that it is clearly defined in context. Now, stating gets a little bit fancier because now we'll actually be able to write our hypotheses, and it's crucial that we write our hypotheses correctly, in particular that we have the correct direction for the alternative, right? If the direction of your alternative is wrong, then everything's going to be off. And we should state the level of significance initially as well, too, though you'll find sometimes sometimes people don't even do it to the conclusion, but you really should do it up front. When we plan, just like before, we'll identify our method and we'll verify that the method is correct by checking all the conditions. And remember, the conditions will always involve randomness, where and this is true of all procedures. We need to make sure that our samples are collected randomly. Remember that we'll also, in connected to randomness, talk about independence, making sure that we have independence in all of our observations and that independence in our sampling. And then finally, we'll talk about something that will ultimately have to do with the shape of the distribution that we're using itself, right? Whether we're using a normal distribution, a t-distribution, and later on a chi-square distribution. Though interestingly enough, AP is kicking out the chi-squares for this exam, so that's a little sad. It makes me sad. But anyways, that's going to be involved with checking the conditions. Then when we're doing extraordinarily minimal amount of work that actually needs to be shown. But you do need to calculate and show a test statistic and then a p-value that you'll be used for determining your significance test, assuming that you're doing the significance test using p-values. And then remember, the test statistic was just a fancy name for a standard score or a z-score, right? It's just measuring how many standard deviations something is away from the mean based on the formulas that are appropriate for the distribution you're using. And then finally, when we make our conclusions, we'll have 2 sentences, one that's purely in statistical language, comparing the p-value to the level of significance, and we'll specifically use phrases like the p-value and level of significance, and we'll compare them and say one's less than the other, so we should reject or fail to reject a null hypothesis, and then in context where we actually talk about it in the relation to the situation we're actually looking at. So let's actually do a full significance test here, okay? So this is the general outline really for all significance tests, but let's do one in particular. And let's start with this particular example if I can find it. Where did I stick it? Aha, here it is. Let's look at this guy. Here we have a machine. In fact, this is a kind of made-up example. We've seen a lot of made-up examples like this, but let's say we had a machine that's designed to fill soda cups to 16 ounces on average, right? That's what it's supposed to do, all right? You can already anticipate it's probably not doing what it's supposed to, right? With the standard deviation of sigma equals 0.2 ounces. And of course, they went out of our way to show us that they're using the symbol sigma, meaning this is a population standard deviation. This is population value, so that's nice. We believe that the machine may be overfilling the cups. Overfilling, that'll be important. To evaluate this belief, we collect a random sample of 40 fills by the machine and observe a sample mean of 16.38 ounces, which is indeed larger than 16, which does suggest we have some evidence that it may be overfilling the cups. The real question, does this provide significant evidence that the machine is overfilling the cups on average? All right, so just looking at this, we'll see that this is asking us to do a significance test about a mean. We're talking about how much are in these cups on average. So let's begin our 4-step process. remember the first thing that we're supposed to do is state. So you don't actually have to write the word state, but I'm going to do that just for the time being, just to try to keep things clear. And I'm going to say, okay, first I'm going to state, right? And to state, the first thing I need to do is to define my parameter. So mu, let's say, is the true average amount of soda filled by the machine, right? How much the machine actually fills the cups. And the key here, the key word here is, and actually you can barely read it, is the word true, the true average. Make there be no mistake that what we're really talking about here is a parameter and not some sample statistic. Okay, so that's the first part, and then we'll actually write our hypotheses. The null hypothesis would be that this machine is functioning as it normally does, and what it's supposed to be doing is filling 16 on average. So we'll say mu equals 16. The alternative, well, we're worried about overfilling the cup, so we'll say that mu is overfilling. That would be greater than 16. So the key here is that the word overfilling led us to have to do a right-tailed test with our alternative hypothesis. Okay, now the last thing we'd want to do is come up with a level of significance. Let's test at, I don't know, alpha equals 0.05. There's nothing specific in the question that told me to do some other level of significance. And I don't see any reason to think too deeply about type 1, type 2 errors in this context. So let's just chill with this and go with it. Okay, so we've stated. Now what's next? We have to plan. All right. First part of planning is identifying the correct inference method. Well, what would be this inference method? Well, let's see here. We're testing something about a mean, right? But there's something very special. Based on what's said here, there's no sample standard deviation given to me. There's only this population standard deviation. So if I think about it, this is going to be a situation where I'm going to deal with the mean, but I'm going to assume I still know a population standard deviation. This means that I'll deal with the mean using the normal distribution, which is always some kind of z interval, or in this case, a z-test. So the test procedure we're actually going to do here is going to be called a one-sample z-test for mu. And the conditions for carrying out something like this are conditions just like we saw when we were making confidence intervals and the such, right? We're going to need to have randomness, and we'll talk about that. We're going to use the central limit theorem, and we're going to assume that in this case that hopefully we have at least 30 things in our sample, and that way we could use our normal distribution. So let's take a look here. Now we're going to plan. Let me write the word plan down. Plan, right? And in terms of plan, the first thing I'm going to say, this is going to be a one sample z-test for mu. Okay, one sample z-test for mu. So let's talk about the randomness condition first, right? Do we have randomness? And the way I check for randomness is kind of hoping, it says randomness. Sorry, my terrible handwriting. Do I see the word random somewhere here? Ah, yes. I see that this is supposed to be considered a random sample of 40 fills, right? So I'll say randomness is satisfied because we have a random sample of 40 fills by the machine, right? So that gives us randomness there. And then let's think about independence, right? We'll have to say, okay, I'm going to write down the word independence. This is kind of connected to randomness. I'll say in terms of independence. In this case, I'm going to have to assume that any time that this machine fills a cup is independent of every other, right? So I'm going to assume that all fills are independent, right? And I'll also assume that this machine will fill the cup way more than 40 times. Remember, we'll also talk about the 10% condition. And in other words, that the 40 fills that we saw is less than 10% of all possible fills. And so, again, we'll make an assumption. We'll assume the machine has more than 40 times 10, which equals 400 total fills. Which I guess, I mean, if a machine can only fill a cup 400 times, what the hell kind of machine is this? Excuse my language. We should probably just get a better machine. So anyways, clearly that seems to be a logical assumption in terms of independence. Now, the last thing we need to check has to do with the shape, right? And the actual distribution itself. And in this case, we'll check the central limit theorem. Central limit theorem. And that's because we're dealing with a situation where we knew the population standard deviation. Okay, so to check the central limit theorem, we're going to check our sample size. I'll use green this time, and let's see here. Was our sample size at least 30? Aha! Our sample size was 40, so we can say since n is equal to 40 is greater than 30, the distribution of our sample means is approximately normal, right? And boom. So here we're being very thorough, and notice that just as always, the planning phase is the most labor intensive and arguably the most annoying part of carrying out this test. Hopefully when you're carrying these things out and you're writing stuff down, you're not using such thick markers as I am, so you can fit things on pieces of paper that I can't, but I'm writing kind of big. So anyways, that's the first 2 steps of the full 4-step process. What's left is mostly the easy stuff now. Where's the actual mathematics? Now, let's carry out the Z-test. Now, to carry out the Z-test, we'll now do, right? We'll first calculate the test statistic. And the test statistic is just a fancy name for a standard score or a Z-score for looking at a particular sample mean relative to everything else. Remember, our ultimate goal, right? And I'm actually showing a little bit more work than I need to here, but our actual goal is to find the probability that X bar is greater than the actual one we got in our sample, which was 16.38. And that probability is the p-value. And so along the way to calculate this p-value, we'll first find the test statistic, and then we'll use the normal distribution to get the actual p-value. So if we were showing all of our work here, being very, very thorough, then we know for a z-test in this situation, we'll put our particular sample mean in context of the appropriate sampling distribution. So we'll say, in general, this would be some x bar minus whatever we hypothesize to be true about our population mean, and we'll divide that by the appropriate standard deviation formula for the sampling distribution of a sample mean. Now, in this particular instance, my sample mean was 16.38, right? Remember that the hypothesized mean that we were dealing with here was the 16, right? So I'll do minus 16. And then the standard deviation of that's appropriate here would be the standard deviation of the population, which is 0.2, divided by the square root of our sample size, which was 40. So let's see what that comes out to be. I'll get out my handy dandy TI-84 plus CE calculator. 16.38 minus 16, which obviously is just 0.38. Why did I even put that in the calculator? I feel kind of foolish for doing that, but whatever. Divided by 0.2 divided by the square root of 40, right? That was our sample size. And Shazam, what the what? Holy moly. That is quite, do you guys see what that test statistic came out to be? That is ridiculous, right? It came out to being 12.02 approximately, right? And actually, usually I'll show more decimal places than that. I say 12.017, but regardless, in this case, it hardly makes a difference. That, my friends, is a very, that's a big test statistic, right? And so do you think we're going to reject the null hypothesis here? Here, I'm almost certain we will. Remember the actual p-value then, which we want is the probability is x bar, right, greater than 16.38, will really just be the same thing as the probability of getting a z-score that's greater than 12.017, you know? And there's almost no chance of doing that. I mean, what am I doing here? What the heck am I doing? Second vars, I'll go to normal CDF. I'll go from 12.017, upper bound might as well be positive infinity, paste, and holy moly. Do you see that p-value? Oh my gosh. You will rarely see a p-value this small, but I couldn't write enough zeros. How many zeros would I have to put before the 1? 32 of them. That's insane. This is about 1.49 times 10 to the negative 33rd, which is very close to, not actually equal to, but very close to actually being 0, right? So, what do you think we're going to do here in terms of our conclusion? Well, before I jump to actually writing the conclusion, let me just show you how there was a really beautiful shortcut way of doing this entire test without sitting here and showing all the formulas. Remember how we used to hit stat and go over to tests? what might be a useful thing for us here in this circumstance? I don't know. How about a Z-test? Yeah, it's what we just did. We're doing a one sample Z-test from you. And so Z-test, yeah, that'll take us where we want to go. So first, if we were to just plug in, say, our hypothesized mean 16, the population standard deviation 0.2, sample mean, which was 16.38, sample size, which was 40, and we picked greater than, right? Now, there's two options. You can either calculate or draw. I'll show you both really quick, but let's calculate. And whoa, check it out. A couple button hits, and there's my test statistic, there's my p-value. And so actually, as it turns out, say you're just taking the test and you're showing your work. The only two things you would actually have to show, even without showing any work at all, would be this right here. Oh my gosh, we're going off the page. The test statistic, 12.02, and the appropriate p-value, which in this case is 1.49 times 10 to the negative 33rd, or approximately 0. The only two things you'd really have to write down when you're actually doing the test is just these two numbers. You should label them, test statistic and p-value. And you could get them instantaneously from the calculator. The only downside to just using the calculator and not showing any formulas is, well, what if you made a mistake? You had all the right formulas, you knew what you're supposed to do, but you typed in the wrong number in the calculator, which is kind of what would worry me. If I got a test statistic like this, I would probably be worried that I made a mistake writing it in the calculator. So I recommend that if you have time, go ahead and show the formulas so that if you do make a minor error, we can at least give you some partial credit. But notice the only thing you need was boom right there in the calculator. Remember, to get it, you hit stat, go over to tests, and in this case, we just did a regular old Z-test. Now, I did tell you I'd show you draw. So if you go to draw, look, it's gonna, oh, look at that, isn't that cute? It drew the normal curve, and it tried to shade in the p-value, but notice it said that the p-value was basically 0, because how much you shaded in, yeah, that's basically nothing. So in fact, the drawing, tells you everything that you need to know as well too, except it gave us a less precise p-value, which maybe we don't care about. It's ridiculous. It's obvious what we're gonna do here. Okay, so let's finish off our test. We stated, we wrote the hypotheses, said the level of significance, we planned, we did. Last step is what? Conclude. All right, let's conclude our test. We're almost done. Remember, I said that you need to make two sentences, right? And so my first sentence is going to be a kind of statistical answer. I'm going to use statistical language. And so my statistical language answer would go something like this. I'd talk about the p-value and the level of significance. I'll say, since my p-value, or the p-value, it's not really like mine, I don't own the p-value, of 1.49 times 10 to the negative 33rd, that's crazy. That's a crazy p-value, man, is less than, it is definitely less than alpha equals 0.05. What do? I reject the null hypothesis. And know that I can just write ho there. I don't need to even write the word null hypothesis. Notice this first statement is entirely in statistical language. It's a statistical reason for what the conclusion that I make. The next part of the conclusion is I'm going to write one that's in context. In other words, I'm going to have it make sense based on this actual scenario, or based on how we defined our parameters. So we'll say, okay, in context, what should I say? I would say, therefore, I have significant evidence. What do I have significant evidence for? Well, I have significant evidence to reject the null hypothesis. I'm rejecting the null hypothesis, and therefore I have evidence in favor of the alternative. So in this case, I have significant evidence that the true average amount of soda in filled by the machine is greater than 16 ounces, right? That would be my conclusion. I have significant evidence that the true average is greater than 16 ounces, which we thought it would be. Couple of things here. It is a possibility we made an error. I mean, even though this p-value is absurdly tiny, we might have made an error. In this case, the kind of error we might have made is a type 1 error, but you know what? We still go with the evidence. And I'm not saying that it's guaranteed that this machine is overfilling the cups, but I definitely can have evidence that it does. Another thing that's kind of interesting is it doesn't necessarily tell me by how much. Right, that's gonna almost hardly read that, but by how much? You might still wonder, well, by how much is it overfilling the cups? Notice that the significance test can't tell us this, right? It's not even giving, it doesn't give like a confidence interval. It doesn't give me an estimate of how much the cups are overfilled. All I do is I can say that it is more than 16 ounces. If I want to estimate exactly how much it's overfilling the cups, then for that, I would need a confidence interval, and that's a different procedure. That's what we learned before, and yeah, we didn't do that here. So anyway, this is, again, a quick video trying to show you the formal procedure for carrying out a significance test. Remember that in general, there's the similar four-step process that we saw before. These are all the things that you're going to have to get done. In this case, we did it for a one-sample Z-test, where all we had to do is really check the central limit theorem and make sure that we had n is greater than or equal to 30 on top of everything else. Remember, when you're doing, you got to show just at least the test statistic and the p-value, and then concluding, you got to have at least 2 sentences. Hope that helps. Beautiful. Good time. What am I even saying? Good times, my friends. I will be happy to answer your questions, and we're going to continue to look at more test procedures throughout the rest of the week. Have a beautiful day. Adios. Giddy the heck up.